Okay, so let's graph one full period of y equals 3 tangent 2x. And you know, mathematicians are lazy. They try to find the sneakiest, maybe not the sneakiest, but the most clever way of doing something, oftentimes anyway. And my clever way of doing this is I'm going to graph you the same picture as y equals tangent of x and adjust the scaling. So here I go. So what were the critical pieces of information we used to graph y equals tangent of x, that first example? We needed what, first of all? It wasn't actually part of the graph. We needed the asymptotes, okay? So for the tangent of x, the main period that we plot for the tangent of x or some variation of that, we graph the period that has the y-axis in between the two asymptotes. And then the two asymptotes are the same distance from the y-axis on either side. So that's something that you can grab a hold of and remember. So one asymptote would be to the right some distance. We'll talk about what that distance is in a second from the y-axis. And the other asymptote will be the same distance. So I'm trying to make these scale marks look exactly the same. And then I'm going to draw vertical lines between them. Dotted because they're not actually part of the graph, are they? They're not actually part of the curve that represents one period of this tangent function. Okay. And then there's 3 points I like to plot. Now in this particular case, the period is not going to be pi anymore, so I don't know what this scale mark is, but I do know it should be halfway between the y-axis and the right-hand asymptote. Likewise, this scale mark should be halfway between the y-axis and the left-hand asymptote of the main period. And then we have a number, a value we plot on the y-axis, and then positive, and then a value negative, same distance away. And so we end up plotting these points. Same as before, what's changed is the scale, so the value of the coordinates of those points are going to be different. We'll talk about that in a second. Now, the picture I draw, though, is going to be this, very, very, very similar to the first picture. And, well, you know what? I do better if I do it from the left. So I'll go this way. It curves ever so slightly through the origin and then up. And you can see the curve a little better if you make the asymptotes a little closer together. But anyway, there you go. Okay, so then I got to be honest with you. I was lazy here. I didn't do anything different than I did in the first example as far as graphing this thing goes. So now we have to find the period and then label appropriately. Okay? So what's the normal period of the tangent function? The normal period is pi. Now I haven't given you a formula for finding the period of 3 tangent 2x, but based on what we did with cosine and sine, and based on how a horizontal stretch or shrink works, what would it be? Pi over 2, whatever the number is right there. What does that mean? That means the entire distance between the asymptotes. So this is worth knowing. The entire distance between the asymptotes is pi over 2, which means half that distance out to this scale mark here is what? Pi over 4. So the equation of this asymptote is it's a vertical line. Vertical lines always have the equation x equals a constant, and in this case pi over 4. X equals pi over 4. And what would the equation of the left-hand asymptote be? Negative pi over 4. And then that's almost the whole ball game, right? Because you can get the other scale marks based on the horizontal placement of those asymptotes. So what would this middle scale mark be? It would be pi over. It would be half of this, so pi over 8. And then this would be the opposite of that, negative pi 8ths. And then what would this value be right here? So this is what we were talking about. Somebody asked me about the amplitude. It's not the amplitude, but this pi over 8, this number that splits the y-axis and the asymptote in half, is the number you could plug into the function And when you take whatever number here is here, in this case 2, times that, 2 times pi over 8 is what? This pi force. And that's the number that makes the tangent 1 when you plug it in. So whatever this value turns out to be, in this case pi 8ths, every single time you plug it into a function of the form a tangent bx, that's the value that's going to make the tangent 1, and then the actual height value will be, it'll be 1 times whatever this value is out front. So it's at a height of 3. The tangent function is at a height of 3 when you plug in pi over 8 midway between the y-axis and the asymptote. And so some people like to create an analogy with that in the amplitude, although it's not an amplitude. And then if this is 3, what would this negative scale mark be? Negative 3. And there you go.